Welcome, everybody. This is Jason, and the name of this week's workshop is What the Flag? And I'm a little bit out of my depth, so I will let my good friend William do the workshop.
Thank you, Jason. More of a presentation than a workshop, and if you have any questions, just jump in and we'll take it slow. So this is a presentation looking at the semantic flag and bitwise operators, as there have been as to what they are. So we're going to start with the flag operators, and in semantics there are three flag operators. The first one is clear flag, which you can think of somebody waving a flag and not waving it. Set flag, somebody with a flag raising it up so you can see it, and somebody asking have they got the flag up or down, which is flag set. But flags are a bit of a abstract concept. Where do we come across flag operators? Most people are familiar with them in the init behaves, where you're doing things like clearing the flag here, which says clear flag, does it number literal 6, does it burn? So it doesn't. So clearing it doesn't burn. If we set the flag 8 in the same thing, which is cannot be stolen, then it cannot be stolen. So and for setting can things appear on end tables, tables, deco slots, that's kind of where we usually come across setting and clearing flags. Beyond that, it's like, what on earth is going on? We're going to have to take a little step back into some theory of computing, I'm afraid. So a bit of background, and the pun is intended. Digital computers store data as on-off, powered up, powered down, positive, negative charge, whatever way you want to look at it, hole, no hole in punch cards if you're that old. So they have one of two states. It's on or it's off, it's powered up, it's powered down, positive charge, negative charge. And a digital computer arbitrarily assigns those states the value of 0 or 1. So digital computers only know about zeros and ones. Humans know about 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but computers only know about 0 and 1. As we've got two values, it's called binary, as opposed to when, as a human, we're dealing with 10 digits. Dec, 10, decimal, base 10. And this is where the word bit comes from. Bit is a contraction of binary digit. So zeros and ones are binary digits or bits. And in a computer, a 0 or 1 doesn't give us a lot of possibilities. So in the early computers, they were combined. So 8 of them were combined into a bigger array. And we created this thing called a byte. And that is a very bad pun. If you take lots of bits, you end up with a byte. But what do all those noughts and ones, 0, 0, 0, 1, 0, 0, mean? So let's go back to decimal. If we have a number in decimal, 1, 2, 3, we tend to read that not as 1, 2, 3, but 123. But if we look at it, at the right-hand end, we have something that represents 3 ones. Then we have a number that represents 2 tens. And then we have a number that represents 100, 100 being 10 times 10. So we're going up in multiples of 10. If we look at 0, 1, 1, 1, 1, 0, 1, 1, or whatever it is in binary, then each of these states only represents 2. So the right-hand digit is representing a single 1. Then we multiply that by 2 for the next one. So we then have 1, 2. We have no 4s. We have 1, 8, 1, 16, 1, 32, 164, and no 128s. And if you add all those numbers up, you also get to 123 in decimal. So 123 in decimal is 011110111 in binary. And that's all we're doing. It's a different way of counting. If we were to write out that number in a semantics program, it's error prone. Did I write down 4 ones or 3 ones or 5 ones? And believe me, it's incredibly tedious. So instead, as programmers, we split those up into groups of 4, and a group of 4 binary digits can represent the numbers 0 through 15, which is 16 different numbers. So it's hexadecimal, hex being 6, dec being 10, base 16. To represent those 16 digits, we can use 0 through 9, but we need 6 more, so we co-opt in A through F, and this is where these weird letters come from. And A is just used to represent 10, B is 11, C is 12, D is 13, E is 14, F is 15. You then get a confusion between 20 decimal and 20 hexadecimal, so we tend to add a prefix of OX to the front of our hexadecimal number. So in binary, 01111011 becomes hexadecimal OX7B. So you can see on the purple we've got 1 1, 1 2, 1 4. So if you add up 4, 2 and 1 you get to 7. And if you add up for the green 1 1, 1 2, no 4s, 1 8. So we add up 8 and 2 for 10 and 1 for 11. And if we look up here, 11 is B, so that's where the B comes from. Almost there. If it's not clear on a binary number, so 01, 101, is that 101 or is it 101 hex? If it's binary, we'll put a lowercase b on the end. And in Microsoft Calculator, if you start it up and you change it to programmer mode, we can actually type in, we can click on there, change that to hex, and we can type in 7B. It will tell us it's 123 in decimal and it's 01111011 binary. So if you're converting between decimal and hexadecimal numbers, or you want to know what they look like in terms of ones and zeros, MS Calculator in programmer mode really is your friend. But at the end of the day, inside a computer, everything boils down to noughts and ones. That's what we're getting now. So going back to our flags. So a semantics flag is a single bit in one of the data holders, be it a local, a temp, a stack object attribute, whatever. And as semantics is a 16-bit language, you can have up to 16 flags per data holder. So if you try and set flag 17, it will fail because there's nowhere to store it. Flags are numbered 1 to 16 from right to left. So the bit on the right is flag 1 or bit 1, and the bit on the left is flag 16 or bit 16. And why do we use them? Primarily as a way of saving memory. When semantics came out, let's face it, Sims came out in 2000 and something or other, it was probably based on a language created in the late 1990s, and back in the late 1990s memory was expensive and wanting to be saved. So if we'd said that in an int have this object can appear on a table, or it can appear on a counter, or it can appear on an end table, or it can appear on a deco shelf, and we'd used a whole stack object attribute or a stack object data value to represent those, we'd be storing only the values 0 or 1, but we'd be taking 2 bytes, a 16-bit word, for each of those values. So those 4 assignments would take a total of 8 bytes. If, however, because they're only zeros and ones, ons and offs, we store them as flags, we're going to shove those 4 flags into a single 16-bit 2-byte value, And then the beauty of it is we actually have 12 flags left over for future expansion. And this is what they're done for. If you're only storing values of 0 and 1, it's much more efficient to store them as flags in a value than as individual numbers. You end up saving quite a lot of memory. And that's why they were done. So a flag is merely a 0 and 1 in a variable, in a local, in a stack object, attribute flag, or whatever. You can still perform other semantic operations on that local, on that temp. So if we set all of a stack object's placement flags to be the value 0, that is the same as setting all of the flags off. So if you wanted to set a lot of flag or every flag off, you don't have to do clear flag 1, clear flag 2, clear flag 3, clear flag 4, all the way up to clear flag 16. You can just do flag value equals 0, and they'll all go off. In the same way, if you set them to the value OXFFFF, which is 11111111, they all go on. So all that's happening is 0s and 1s are being set into a value. And our example a couple of screenshots ago was we'd set the table on, we'd set counter on, we'd set low table on, and we'd cleared all the others. And because of the flag values being 3, 4, and 8, you see we've got flag 1, flag 2, flag 3 is on, flag 4 is on, 5 is off, 6 is off, 7 is off, 8 is on. So all the others are cleared and set. So if we did stack objects placement flags OOX8C, it's exactly the same as what we'd had before. Set table on, set counter on, set low on. But we're doing it in one operation, not 4 or 5 or 6. And that's all flags are. They are bits within a word, so you can have a maximum of 16 in any one flag operations. Clearing a flag is setting the bit to 0. Setting the flag is setting the flag to 1. And flag set is saying if the bit that's representing this flag is a 1, return true, otherwise return false. Which is all, he said, that is happening. So yeah, it's maths, yes, it's computing, but that's all flags are. Any questions?
The 8C one, that is essentially, so if we enter the 8C into the operands, it's going to set it for example, regular table, low table, and counter, and then clear it for all of the others. So we can enter this one command line and then not mess with adding it for every single type of surface.
Yep.
Okay.
So all we've got here is the 8C. We use Microsoft Calculator or whatever to convert it into binary. And then you just literally count from the right-hand end that right-hand digit is flag 1, the next is flag 2, the next is flag 3, flag 4. And when you look in the init you'll see it will say, it uses a bcon const value. So it will say set flag allowed height end table, and the end table value is coming from a bcon const, which is just the value 3. Yeah, so it's effectively saying set flag 3 on, and that's all it's doing. It's just setting ones and where's my cursor gone? It's just setting ones and zeros. We'll look at clarity and what's better to do, but yes, you could compress 6 or 7 operations for setting and clearing flags as to what an object is allowed on down into one assignment of a hexadecimal value. So looking at Rachel's comment, 0 is black and 1 is white, and yes, it's the same thing. It's whether something is on or off within a color chart. So yeah,
Oh, that's cool.
color values work very similar way. If you look at what categories do clothing come in, is it everyday, is it outerwear, is it swimwear, is it pajamas? Those are just flags, and the numbers that you're adding in there are just representing the flags. Again, which age are you looking at? So young adult is it 48 hex? So the 8 is the adult bit and the 4 is the young adult. If you wanted to add in elder, which is the next one up, I believe you end up with 5-8 in hex, and that's because it's setting a different flag, and it's changing the 4 into a 5. So it's just flags being set, just bits being set. So we're now going to wander off into the realms of bitwise operators. And the way we get there is we're going, well, what if we want to toggle a flag? That is, if it's on, we want to set it off, and if it's off, we want to set it on. We could do 3 lines of code, which says, well, if my flag is set, I'm going to go to 5, which says clear that flag, and then exit. And if it's false, I'm going to go to the line that says set that flag. That's fairly clear. We could do that. Or we could wander off into what are called bitwise operators. And having looked at computers and maths, we're now going to look at language semantics. So our bitwise operators are called AND equals, OR equals, and XOR equals. What on earth does that lot mean? We're going to deal with our toddler. Would you like tea and cake? Quite clearly you're expecting to get both. If you put your own shoes and coat on, we'll go to the park. You've got to have both your shoes and your coat on before we go out. And we can represent this as what's called a truth table. So as you can see, I've got coat here. If it's off, then it doesn't matter about the shoes, we are staying home. We look at our shoes. If our shoes are off, doesn't matter about our coat, we are staying home. It's only if our coat is on and our shoes are on that we're going to the park. Typically we don't write them out with words, we translate that into numbers. So off translates to 0, on is 1, and staying at home is the bad thing, so it's a 0, and going to the park is the good thing, so that's a 1. So we end up with this thing called a truth table, where you can say and if my one value is 0, one value is 1, 0 and 1 is a 0. But basically it means you've got to have them both. Both ones get a 1. That's the easy one. If we look at OR, so you must stop if the lights are red or there is someone crossing. Quite clearly we can have both here. So we have to stop if the lights are red, not unreasonable. We have to stop if there's already somebody on the road crossing in front of us, we don't want to kill them. If the lights are red and there is someone crossing, then we also stop. But we can also have the phrase in English, you can have a biscuit or a cake bar. Now, you might want both, but you're not getting both. So you can have one or the other. And in programming terms, the first case where you can have both is known as an inclusive OR. And the second one, where you can't have both, is known as an exclusive OR. And again, we can represent these up as truth tables. So if our lights are green and there's no person, we can go. If our lights are red, we have to stop, regardless of whether there's a person. If there's a person, regardless of the lights, we stop. So this is, again, translating it into numbers. 1 and 1 is 1, 1 and 0 is 0. It's the either. Yeah, we need either of them to be a 1 and we'll get a 1. The exclusive OR, what we call XOR, is that other case where if you've got both set to a 1, the result is actually a 0. And it tends in English to be one or the other. Are bitwise operators, they're called bitwise operators because they're not acting on the number as such, they're acting on the individual bits individually. So if we assigned local 0 to be 0x0053, which is this in binary, and we then AND that with 14A, and 14A is this number 000000101001100. You can see why we don't say that a lot. Anywhere where we have both ones in both of them, we get a 1 in the result. So starting from the right hand end, a 1 and a 0 gives us 0, 2 zeros is 0. We've got 2 ones where the greens show, and the same. So the final value is this 44. And that's all it's doing. If we do that for a 4 with the same values, with an OR, wherever we've got a green 1, we end up with a green 1 in the answer. So it doesn't matter if we have a 1 and a 0, or a 0 and a 1, or a 1 and a 1, we always end up with a 1. And that's all that's doing. It's just doing it across the bits. And last but not least, if we look at XOR, only where we've got different digits, so a 1 and a 0, or a 0 and a 1, do we end up with a 1. If we have 2 1s, we get a 0. If we have 2 zeros, we get a 0. The interesting thing about XOR is it doesn't matter what you XOR with a 1, you get the opposite value. So 0 XOR 1 is 1, and 1 XOR 1 is 0. That's how you can toggle your flag. So if we wanted to toggle flag B, which is value O or OO in hex, XOR in that will toggle it. So if the flag was on, it would go off. If it was off, it would go on. And that's what you can use bitwise operators for. Now, would I actually do this? I personally think that the pre operation code is actually clearer to follow and easier to understand, and is more likely to be understood when you come back to it than that magic of using an XOR. I'd probably only do that if I needed to toggle many flags at once. If I wanted to toggle 4 or 5 or 16 flags, toggle every flag in a word, I'd probably use XOR, because if I had 12 flags to toggle, 12 times 3 operations is 36. By the time I've written something out 36 times and copied and pasted it, I will have certainly forgotten to have changed one of the values, and I will have introduced an error. So if I was doing a lot, I'd probably use the XOR. If I'm only doing 2 or 3, I'd do them explicitly. Which also comes back to in the init bhav, would I take all the set end table, set low table, set deco shelf? I personally think that is easier to read and understand than going, oh, I'm going to set it to value 0x87. Because you can't put comments in semantics. You can't say this is all values on, this is these values on, and other values off. You'd have to go back and convert that back to binary and then look it back up in a table. I would stick with the 6 or 7 lines in the init bhav that said set this flag, clear this flag, end table, set low table, set coffee table, clear shelf, clear on the ground. I think that would be easier to read and come back to. So, will you ever use these operators? Flags, yes. Bitwise operators, probably not. I actually went through every single bhav within the Maxis Ultimate collection code to find out how often the operators were used. And if we look at things like assignment, they are used, 1.5 million times for almost 54% of the uses of operators. If we go all the way to XOR, which is used 1,535 times, 0.05%. If we add XOR and OR up together, we just get to 0.1%. 1,000th of the operators in ultimate collection are the 3 bitwise operators. Whereas set flag is number 4 in the list. And clear flag and flag set are quite high up as well. They've got reasonable percentages. They're 1.5%. So, are you ever going to use these? Probably not. Do you now know what they're for? How they come into bits? Yes. Can you forget all of this? Almost certainly. And that's it. So, any questions? I've stunned you into silence.
Forgive me, math is like not my favorite thing. This is very mathy.
Oh, it is. It's because it's confusing.
Yes.
Math is my thing, but more like finance math.
Oh yeah, this is a whole new thing. So when you code your mods, do you use these, or do you more likely use like the whatever we were looking at before, like the behave lines? I don't know if that's the correct term,
I have used XOR once. I actually looked in my own code. I've used it once. And again, that was because I was toggling a lot of flags at the same time. I needed to toggle. It was in it's my sick pay mod or whatever it was, and I needed to toggle whether a teen could look after a child or a young adult or an elder or a adult or the nanny or whatever, and it was like I wanted one that said flip what everybody can do. So I was flipping 6 or 7 flags at the same time. So I used XOR. I've used it once.
Sorry, go ahead.
No, that's it. Okay.
Jason? I was going to say, it seems like it's very practical, but only in specific situations.
Yes. It's one of those that when you need it, it's useful to know about because it will save you a lot of lines of code. But I personally think in terms of readable code and will I be able to understand what I was doing when I come back and look at this in 2 months' time, the set flag, clear flag, flag set operators are much better to use.
Yeah, for example, if I saw this in an object placement, like allowing an object on certain surfaces, I most likely would not know how to interpret it without this workshop.
Yeah. And if you wanted to add another, if you say, oh, well, it's enabled for table, but somebody's forgotten to enable it for end table, you'd go into SimPE, you'd just hit, insert on true, like in my SimPE editor 101, and you'd just go into the wizard and you'd change from the table to an end table and you'd go, yeah, I know how to do that, and I can come back and I read it and yeah, that's quite clearly correct. Otherwise you'd have to go and look at this number and go, okay, what does that represent? Oh, I've got to go and look up this manual table somewhere. Oh, end table is flag 4, so I've got to work out what setting a 1 is on that, and yeah.
Yeah, and if it were me, if it were just the average creator, I would duplicate or I would insert through that command line, and then I would just add the extra set flag for end table and for counter or coffee table or whatever.
Yeah, and if you suddenly go, oh, somebody said this can't be placed on the ground because they've cleared the ground flag, oh, I want it to be placed on the ground, you've already got the line and you just go, well, it's not clear flag, it's set flag.
So this might be out of scope, but like for the longest time, OMSPs, I get annoyed because like on the shiftable OMSPs, I can't put a light. So would I just go into those OMSPs, or would I go into that light and flip a toggle like saying this can be put on an OMSP, whatever the OMSP surface value is?
The OMSP should behave as coffee tables or end tables or tables. If you can't put something on them, this is what Radira was discovering earlier, it may be that the support weight of the OMSP is wrong and the item you're trying to put on it is too heavy.
Oh.
But
Yeah, I've never been able to put lights on like OMSPs. There's like a different thing. There's like a pole OMSP I can put them on, but not the tray OMSPs. So you're saying that tray OMSPs might not be equipped for the weight of the
Yeah.
light, the lamp.
which OMSP specifically, Rachel? Because
The acid lucidity shiftable OMSP set
okay.
mostly.
Silent lucidity. No, I know for a fact all of those are set as 8, which is end table. So something that can only be placed on the ground, you wouldn't be able to pop it into that slot. You would need to go back and modify the object, not the OMSP.
Okay.
Yeah,
Well, they're lamps, so they should be on end tables. It's just they don't ever.
but even if the lamp can be
snap.
placed on an end table, the end table's support weight may be higher than the OMSP's support weight, so the weight of the lamp won't go on the OMSP. Yeah.
So you would
Okay.
just add the command line to the OMSPs and it behave to bump up the support strength.